Okay, let's take a deep dive. Today, we're stepping back, quite a way back, actually, to a really fascinating moment in mathematics.
Hmm.
We're looking at set theory, specifically through a paper by, well, the brilliant Kurt Gödel from 1938. It was communicated to the National Academy of Sciences.
Right. And set theory, I mean, for a lot of mathematicians, it's sort of the bedrock, you know, the foundation.
Absolutely.
But even down there at that foundational level, there were some, let's say, tricky questions, big ones, and axioms, these fundamental statements that were, well, causing quite a stir.
And Gödel's paper jumped right into the thick of it.
It really did.
Yeah.
It tackled two of the most famous, maybe infamous ones.
Yeah.
The Axiom of Choice, or AC, and the Continuum Hypothesis, GCH.
So our mission today, for you listening, is to really try and unpack Gödel's result here. It was incredible. He didn't prove, that set theory was absolutely perfect, but he showed something really key, a relative consistency.
That's the crucial word, relative.
Yeah, he showed these controversial ideas, AC and GCH could actually coexist peacefully with the standard rules of set theory. Right? If those standard rules were already consistent themselves. It's like a conditional peace treaty, you could say.
Exactly. He wasn't making claims about the absolute consistency of the whole structure. That's another saga entirely.
Still a huge question.
Right. What he proved was that adding these specific controversial bits doesn't suddenly introduce a contradiction if one wasn't already lurking there.
Okay. So let's get into the details then. What exactly was the core theorem, the big result in this 38 paper?
So the main theorem says this. If you take a standard system of set theory axioms, like the ones von Neumann or Fraenkel were using, or even from Principia Mathematica, without the axiom of choice built in yet.
The generally accepted ones at the time?
Exactly. If that system is consistent, then it stays consistent even when you add several quite powerful propositions all at the same time.
All at once. Okay. And what were these propositions? You mentioned AC and GCH, but was there more?
Yeah, it's a package deal he showed was safe to add. The list included 1, the axiom of choice itself. That's the one saying, roughly, you can always pick one item from each set in a collection, even an infinite collection. Sounds obvious, maybe.
But it leads to some weird places, mathematically speaking.
Very weird places. Then 2, the Generalized Continuum Hypothesis, GCH. This is about the sizes of infinity.
Right. Are there infinities between the size of the whole numbers and the size of the real numbers, for example?
That's the classic continuum hypothesis. GCH generalizes it. It basically says there are no intermediate infinite sizes. You go from one infinite size, say our left null, the next size up is a left 1, which is 2 to the power of a left null, and so on. No gaps.
Okay.
And then 3 and 4 were a bit more technical, involving the existence of certain let's call them mathematically pathological sets.
Like what?
Things like non-measurable sets you can't assign a standard size or length to with specific properties when you project them. And also sets of real numbers that are like continuum size big, but internally quite sparse. They don't contain a perfect subset, which is a kind of dense structure.
Wow. Okay, so that's quite a mix. AC, GCH, and these stranger sets.
Yes. And he showed adding all of them together wouldn't cause a contradiction if, and it's a big if, the original system T was consistent.
Which brings us back to that word relative. It all hinges on the starting point being okay.
Precisely. It's an if T is consistent, then T plus these axioms is consistent kind of statement. And importantly, his proof was constructive.
What does that mean, constructive here?
It means if, hypothetically, someone did find a contradiction in the bigger system, the one with AC and GCH and the others, Gödel's method provides an explicit recipe, a way to translate that contradiction back and find a contradiction in the original smaller system T.
Ah, I see. So it's like saying, look, if adding this stuff causes a problem, it must be because your original setup already had a hidden problem.
That's a great way to put it. If the new room makes the foundations crack, the foundations must have been flawed to begin with.
Okay, that makes sense. So the big question then is how? How did he pull this off? What was the technique?
The absolute key was his method. He constructed a specific mathematical world, a model for set theory.
A model, like a mini universe built according to the rules.
Exactly. But crucially, he built this model using only the axioms from the original, supposedly consistent system T. Nothing extra smuggled in.
And what was this model made of?
It was made of what he called mathematically constructible sets.
Constructible sets. Okay, what does constructible mean in this context? Is it like building sets piece by piece?
Sort of, yes. He used the term quite precisely. Think about building things in levels or layers. You start with some basic elements, maybe the empty set, that's level 0. Then you form all possible sets whose members are drawn from level 0. That's level 1. Then sets whose members are from level 0 and 1, that's level 2, and so on.
Like building with Legos, kind of?
A bit like that, yes. This idea has roots in work by people like Bertrand Russell, the ramified hierarchy of types. But Gödel took it much further.
How so?
He extended this layering process not just through the finite levels 0, 1, 2, 3, and so on, but into the transfinite.
Transfinite orders? Whoa. So beyond infinity, level omega plus 1.
Precisely. You keep building stages indexed by ordinal numbers, going way, way up. And this extension into the transfinite was absolutely critical.
Why was going transfinite so important?
Because standard set theory axioms, things like the power set axiom or separation, can seem impredicative. They sometimes define a set by referring to a collection that the set itself is supposed to belong to. It feels a bit circular.
Right, like defining something in terms of all things of this type, including the thing you're defining.
Exactly. Gödel's Constructible universe, built layer by painstaking layer through the transfinite ordinals, avoids this. It's strictly predicative, or, as he put it, semi-intuitionistic in its construction. Everything is built from below.
Okay.
And it turns out that this carefully built universe of only constructible sets is actually rich enough. It satisfies all the standard axioms of set theory, system T. He could even prove a kind of axiom of reducibility within it for high enough orders.
So he builds this very structured, layered universe using just the basic rules, and within that universe,
a very specific statement turns out to be true. He called it Proposition A.
Proposition A, what did it state?
It stated simply, every set is constructible.
Which makes sense, right? Because he deliberately built the universe only out of constructible sets.
Exactly. So Proposition A has to be true in the model. And because the model itself was built using only the axioms of T and shown to satisfy T, this means A must be consistent with T. Adding A doesn't break T, because A is just a description of how T works inside this special model.
Okay, A is consistent. How does that get us to AC and GCH being consistent?
Here's the beautiful connection. Gödel then proved that all those propositions we listed earlier, the axiom of choice, the generalized continuum hypothesis, those weird sets, they can all be logically deduced from Proposition A. They are consequences of assuming that every set is constructible.
Wait, hang on. Let me see if I've got this.
Go for it.
He builds a model, the L universe of constructible sets, using just the basic axioms T. Inside this model L, the statement, everything is constructible, A is true. So A must be consistent with T.
Perfect so far.
And then he shows that AC and GCH are logical consequences of A.
Yes.
So if A is consistent with T and AC, GCH follow from A, then AC and GCH must also be consistent with T. Is that the logic?
That is precisely the argument. It's a brilliant piece of logical bootstrapping.
Wow. Okay. Can we get a bit more intuition, maybe? Why would GCH, the continuum hypothesis, follow just from assuming all sets are built in this layered, constructible way?
It's a bit subtle, but think about the process. Because you're building sets in such a regimented, step-by-step fashion, defined only by things built at earlier stages, it puts constraints on how many new sets you can actually form at each stage, especially when taking power sets. Sets of integers, for example, all get constructed relatively early, below stage omega. Sets of integers appear by stage omega 2, and so on.
So it's very orderly.
Extremely orderly. This orderliness essentially limits the bushiness of the set hierarchy. There just aren't enough constructible ways to make sets of intermediate sizes between the standard LF numbers. The construction process itself enforces the GCH pattern. You only generate the next smallest possible infinity when you take power sets.
Okay, that helps. It's like the building code is so strict it only allows certain sizes.
That's a reasonable analogy, yes.
So, stepping back again, what's the bigger picture here? The significance of this 1938 result?
Well, Gödel himself felt that Proposition A, every set is constructible, might offer a kind of natural completion to the axioms of set theory.
A completion?
How so? It provides a definite answer to the question, what is an arbitrary set? Instead of some vague notion, it says a set is something that can be constructed in this specific transfinite hierarchy. It tames the wildness a bit.
And this idea A, its consistency seems pretty solid.
Gödel thought so.
Yeah.
He pointed out that the proof showing A is consistent with T holds up even if you add stronger axioms of infinity to T, like assuming the existence of inaccessible cardinals.
Which suggests.
It suggested to him that maybe the consistency of A was somehow absolute, although she was careful to say that term didn't have a precise mathematical meaning back then. It felt fundamental.
But still, always with the caveat that for AC and GCH themselves, it remains a relative consistency proof.
Absolutely crucial to remember that, because the model L itself, the whole constructible universe, is built using the transfinite methods allowed by the base system T. You need T to be consistent to even talk about L being a valid model.
So the final conclusion rests on that initial assumption about T.
Correct. If T is consistent, then T plus AC plus GCH plus those other bits is also consistent.
Okay. So wrapping this up for you listening, what we've walked through is this truly elegant proof by Gödel from 1938. He showed that two of set theory's most debated statements, the axiom of choice and the generalized continuum hypothesis, won't cause a contradiction if the basic rules you start with are already contradiction-free. The way he did it was by constructing this special universe, the universe L of constructible sets, where, remarkably, AC and GCH just turn out to be true.
It's a fantastic illustration of how mathematicians use models, these concrete examples within a system, to explore the relationships between potential axioms, even in the incredibly abstract realm of infinite sets.
And it leaves us with a really provocative thought to ponder. Gödel showed AC and GCH are consistent with standard set theory, relative to T. But decades later, Paul Cohen proved something equally profound. They are independent.
Meaning, you can't prove them or disprove them from the standard axioms, like ZFC, which includes choice.
Exactly. So if these statements, which feel so fundamental to the nature of infinity in sets, are actually undecidable within our standard framework, what does that tell us about the limits of that framework? What does it say about mathematical truth itself, especially when dealing with the infinite?